Okay, so our last panel is here for to talk about marine life. I don't know if anybody ever thought that the supply of marine life in the ocean was inexhaustible or not subject to the stresses that humans can put on it, but if not, by now we probably are keenly aware of this issue, and it only gets more keen. So this panel will talk about that, and here to moderate is John Mandelman, who is the Vice President of the Anderson Cabot Center for Ocean Life and the Chief Scientist at the New England Aquarium.
Thank you very much, John, as well as to the other symposium organizers who've done a tremendous job putting this together, as well as to Linda Cabot at Anderson for the support for this symposium. For me personally, it's been an absolutely amazing day. I've learned a tremendous amount, and I feel honored and privileged to be a part of it and to have heard so many of these distinguished speakers that we've had here today. I'd like to just take a second before I introduce our speakers for this panel to reflect a little bit on the sessions that we've already had to tie it in full circle to where we're about to go now. And I think back to the Origin of Life panel that started the day, and then we ended up working into the physical interaction between the oceans and our climate. Now we're going to kind of come full circle. We're going to look back at that life in the ocean, and we're going to take a little bit of a look at how these pressures and impacts, disturbances, acute and chronic, although I think our panel is primarily interested in chronic stress, or maybe some acute disturbances that come along with it, but and how that impacts the oceans, how that impacts the ecosystems and the species that inhabit our oceans. So one note that I found really interesting in thinking about the oceans and reflecting earlier was Dr. Gergis's talk. He talked about the incredible diversity in form and function in our oceans. There is in every nook and cranny, every possible organism you can imagine, just in terms of size, shape, mechanics, physiology, the ability to withstand some of the pressures of living in the ocean already. Even without human impact, it's not an easy place to live and evolve. So the ability to respirate, osmoregulate, locomotory skills, all these things, there's just an amazing diversity in the ocean. So now you throw in human anthropogenic disturbances into the mix, and it's really quite incredible how much damage that can cause over a very short time span. And as you'll see momentarily, there are case studies from right here in our backyard. I think it was Lynn Talley's talk where she mentioned how climate change is really, or I should say global warming is really ocean warming, as so much of the warming is reflected in our oceans. And we've no better a case study than right here in the Gulf of Maine. And that's a good way to lead into our first speaker for this panel. Dr. Andy Pershing is the Chief Scientific Officer up at the Gulf of Maine Research Institute, also known as GMRI. He also runs the Ecosystem Modeling Laboratory there. And his expertise is looking at the causes and consequences of climate trends and climate change here in the Gulf of Maine and the Northwest Atlantic in general. He's done a lot of amazing work in that realm, which he'll talk to you a little bit about today. Moving on to our second speaker, Dr. Ann Cohen from the Woods Hole Oceanographic Institution. Ann is an internationally renowned scientist who does work looking at the effects of ocean acidification and warming as well, right, on ocean inhabitants. Predominantly coral reefs, and then as you'll learn today, some of the animals here in our own backyard. And then finally, we're going to get to hear Dr. Chris Clark. I'm sorry, Chris, I'm going to have to read this. So your title is a little complicated. So just Chris. All right, Chris. Dr. Clark is the I.P. Johnson Founding Director at the Cornell Laboratory of Ornithology's Bioacoustics Research Program and a senior scientist in the Department of Neurobiology and Behavior at Cornell. Dr. Clark, I know of his work because he's worked very closely with my close colleague, Dr. Scott Krause at the New England Aquarium for years looking at the endangered North Atlantic right whale. And while I think Chris's basic expertise is looking at acoustic signaling or communication between organisms, he's applied a lot of novel and very sophisticated acoustic technologies to addressing some of the big conservation issues facing our oceans, especially on endangered species, including whales and birds. So it's a real nice, diverse mix of speakers today, but I think touching on some different topics, and I really hope you enjoy it. With no further ado, I'll welcome Dr. Pershing.
All right, thank you for coming, and thanks for inviting me. And it's great that everybody stuck around after coffee. So my name is Andy Pershing. I'm the chief scientist at the Gulf of Maine Research Institute, which is just up the road in Portland, Maine. So I'm going to give just an overview of a few things. I'm going to talk with a couple of basics of climate change and really try to pick up some threads that, that some of the earlier speakers presented. I'm going to then turn to our local waters and think about the impact that we've seen of global warming and the warming trends that we have observed here in the Gulf of Maine. And then I'll talk about the impact of those temperature changes on cod. Lobsters had to be cut. I'll talk a little bit about lobsters, but I'm not going to give the full lobster story today. And then I'll talk about how we're thinking about adaptation in terms of fisheries and natural resources. And I hopefully it'll be a nice complement to the great talk we heard about adaptation on the human infrastructure side. So this is the famous Keeling curve. Everybody's seen this, unless you were a caveman who was just, recently de-thawed, in which case this is why you were recently de-thawed. But the previous speakers did a great job, I think, talking about the consequences that rising levels of carbon dioxide are having on our planet in terms of warming temperatures, impact in vulnerable places like the Arctic, CO2 dissolving into the ocean and things like that. It's really easy, though, to think that these are surprises, that somehow we're just discovering this. And of course, there are surprises, and it's really important that we need to document what's going on out there. But one of the reasons that we're doing this, that we're trying to document all this work, is that it allows us to actually test models and predictions that were put together 20 or 30 years ago. And so what I want to do is actually walk you through a very quick test of a climate model, because I think it's really informative to think a little bit that the science of climate change is not a new science. In many ways, we're following threads that were laid down over 100 years ago as far as the role that carbon dioxide plays in making this planet habitable. So I'm going to start with we're going to start by trying to test a prediction by James Hansen. So in 1981, Hansen wrote a really influential paper in Science magazine where he was working with an early climate model, and he made a prediction based on the trends in carbon dioxide that he was seeing at the time and predictions on how people would use carbon over the next 30 or 40 years, that anthropogenic carbon dioxide warming should emerge from the noise level of climate variability by the end of the century. So really what he's saying is that by the end of the 20th century, that we should be able to look at the record of temperature on the planet, and we should be able to clearly see that there's a warming signal, and we should see that signal standing out even among the variability that we have. Then he also made predictions, and these should sound familiar, the creation of drought-prone regions in North America and Central Asia. So think about the talk that talked about the amplification of the hydrologic cycle, and the opening of the fabled Northwest Passage. Think of the previous talk with the very depressing shot of the cruise ship in the Northwest Passage. So in 1981, this is the temperature record that Jim Hansen would have had available. In fact, his group was really instrumental in putting together many of these global data sets, including this one. And so you can see in 1981 that the temperature in that year was only slightly higher than the temperature that was measured in about 1942. And so yes, you could say, well, maybe there's a hint of a trend, but there's also quite a bit of variability. It would be very hard to say that there's a conclusive trend in that data. 10 years later, some continued warming, but I don't know, maybe it's going down. Things are cooling off. It won't be too bad, right? OK, well, of course it's worse than that. By the year 2000, we're now able to see a very clear trend in this data set. So in many ways, Hansen was starting to make predictions using some of the early climate models, and we can now test those predictions. And Hansen was right. And of course, it continues. And we're now faced with the warmest year ever that humans at least have measured on the planet. And we're thinking about the consequences of persistent drought in the Southwest. We heard a great talk about the consequences of loss of sea ice in the Arctic and cruise ships going through the Northwest Passage. But one of the reasons why I like to include this story in my talks is because I'm going to take some of the temperature records from climate projections and start to think about the impact that the predicted temperatures are going to have on species that we care about. And so that Hansen story is meant to give you a little bit of confidence that global climate models actually can say something meaningful, that we're not just making them up, it's not a Chinese hoax, that there's real science behind this, and that we know what we're doing. So of course I'm showing two different scenarios. The red one is the high CO2 business as usual emissions pathway that we're on. The blue one is a very optimistic scenario where CO2 emissions are cut way back. And they have very different pictures of what the future temperature of the planet will look like. But one of the things I want to highlight is that over that first 30-year period, those two lines are almost exactly the same. It is very hard to distinguish them. So we really are dividing the world into these two periods, into this initial period of the next 20 or 30 years where we really have to adapt to the changes that are already baked into the system. One of the things I like to say is that the temperature that we have on the planet this year is actually a consequence of carbon dioxide that was emitted when Nirvana was on tour in the early 1990s. But then we start to think about choices that we can make that will play out then towards the end of the century. So I'm going to talk about a temperature story, and Anne's going to pick things up with a story about ocean acidification, and we just heard a great talk on sea level rise. So this is the Gulf of Maine. It does bear the name Maine, but I think it's really important to remember that it's not just Maine, that it's Massachusetts, it's Nova Scotia, it's New Brunswick, and yes, even New Hampshire gets a piece. So it's a really important body of water, and it's been a very important and influential body of water in the settlement of New England. So this is the temperature record from the satellite data going back to 1982 of sea surface temperature in the Gulf of Maine. So I'm showing it on almost a weekly scale, so a lot of variability. That's that blue line in the background. If you begin to take annual averages, you get the gray dots, and you can see there's some pattern, right? There's kind of maybe a 5-year cycle or so that's going on in the 1980s, a bit of a jump around 2000, and then things have warmed up over the last few years. And we can start to do some statistics. So if we fit a line, that black line has us warming at a rate over this 34-year period of 0.04 degrees Celsius per year. Okay? That's hard to kind of fathom what that means. That's 4 times the global average rate. The global average ocean warming rate is 0.01 degrees Celsius per year over this same period. So we've been warming over this period at 4 times the global average rate. But it gets better. So from 2004 through 2013, I highlighted this 10-year period because it was something that it was a feature that really stuck out once we started looking at this data. And over that period, we warmed at almost 1/4 degree Celsius per year over that 10-year period. If you map the trends over that 2004 through 2013 period, so red in that figure at the top is an area that has a steep warming trend. Blue would be an area that has a cooling trend over that 10-year period. You can see that there's a little bit more red, but it's probably hard to see than blue. But the Gulf of Maine and our region really stands out in terms of being bright, bright red, along with places like I guess I have a pointer, like the Barents Sea off of Norway, region off of Australia, right? So these are all areas that had similar trends over the last 10 years. But the Gulf of Maine still stands out. So if you view this as a histogram, we're way out here on the right-hand side of that distribution, which leads to the statistic that over that 10-year period, we warmed faster than 99% of the global ocean. It was a 10-year warming trend, or 10-year increase in temperature that very few large marine ecosystems have ever experienced. So what has been driving that trend? Well, in the Gulf of Maine, we're just this really interesting place on the planet. We're right at the boundary between cold water and warm water, and between cold air masses and warm air masses. And the shifts in those warm air masses or cold or water masses has a big impact on the temperature that we have. So in particular, we have a cold current that comes in from Nova Scotia. We have warm water that can come in from off the continental shelf. And then we have the Gulf Stream, which is riding out here off of the continental shelf. We have seen over the last few years an increase in the latitude of the Gulf Stream. It's been pushing further north. And when that happens, we get a characteristic series of changes in the circulation. We get a decrease in that cold current, and we get an increase in the supply of warm water. So it's a lot like a bathtub where you adjust the temperature by turning the warm up if you want it to be warm, and you can turn the cold down if you want it to be really warm, right? And so that's what's been going on in the Gulf of Maine. But why has the Gulf Stream been changing? Why have these currents been changing? Well, here's the map that I previously showed you that showed the warming trends over the last 10 years. Here's a map that Vint Saba, a colleague from the Geophysical Fluid Dynamics Lab, had in his paper, and he allowed me to modify it. And what I did was I took the warming trends from his paper, where he was running a very high-resolution climate model, the only one that actually can resolve the continental shelf in our area and really get that shelf circulation that's so important to maintaining the temperature in the Gulf of Maine. It's the only model that can get that right. And so what I did was I took the warming trends out of his, that he was projecting, and I just divided by the mean trend. So the gray area up here off of Greenland is an area, it's not that it's cooling, it's just not warming as quickly as the global average, whereas the Gulf of Maine is warming faster than that global average. And so notice the correspondence between the two images. Both of them have this warm, cool, warm, right? Warm, cool, warm pattern. Okay, so we are seeing very similar dynamics playing out right now to what the climate models suggest we should see over the next century. And the mechanism behind that that's in the models and we think also in the data is related to large-scale changes in the North Atlantic circulation, ultimately tied to increases in freshwater supply and melting in Greenland, changing this meridional overturning circulation and causing, instead of the ocean going up and down, right, where you're sinking at the poles and then rising elsewhere, we're putting more energy into going around and around, which tends to kick that warmer water into our region and reduce the supply of cold water. Okay, so now for the biology, since this is a biology panel. So I'm going to talk in depth about cod because it's arguably the most important fishery in the United States. It was the first export from New England. I heard somebody say that the English made more money off of cod exported from New England than the Spanish did off of the gold that they were getting from their colonies in South America. In the late 1800s, after the Civil War, the US had a bounty on cod. We were catching over 70,000 tons of cod from this Gulf of Maine stock in a single year. So remember that number. In 2014, catch limits were reduced to about 350 tons for the Gulf of Maine stock. So a very, very steep decline in this population. And here's what that steep decline looks like. So we had more fish in the early 1980s. We had less fish in the 1990s. And then we have this big decline that started in the late 2000s. Well, what was driving that decline? Well, one of the things that we look for when you're trying to diagnose what's going on with a fish population is you look at the number of new fish that are coming into the population. We call this recruitment. So this is an estimate of the number of new fish that are being recruited into the population, and you can see it has a lot of parallels with this, with the decline in biomass. But that's kind of what we expect. If you have fewer females, you're going to get fewer babies, right? And so in part, some of that is going on in here. So what we did was we took the data up through 2004, before the onset of this rapid warming, and we fit two statistical models that were trying to predict the number of new fish entering the population based on the number of females in the population. So if you have, and then we fit another model that included a temperature effect. Okay, so we have two different models. Both of them do almost equally well during this period. But they perform very differently in this when we confront them with the new data after 2004. If we don't include that temperature effect, we greatly overestimate the recruitment in the population. As a consequence, we greatly overestimate the potential productivity of that stock. And if we include a temperature effect, we actually explain the decline of cod. So temperature was a major contributor to the decline in recruitment and to the decline in this population. But it wasn't just temperature alone. It was really the interaction between temperature and people. So fisheries management is meant to be a negative feedback loop, meaning that if there's a change in the population, let's say there are fewer fish, we pick them up in our sensors and in our process called the stock assessment, and we say, oh, there are fewer fish. We then pass that through the management machinery, and at the end, we come up with quotas or regulations that reduce the fishing pressure on that stock and should allow that stock to increase. Well, over the last few years, we've been in this cycle where every time we look at the stock, there are fewer fish than we thought there were. And not only that, there were fewer fish the previous year than we thought we were when we looked at them then. Okay, very, very challenging. And what our study shows is that the ocean was really changing the dynamics faster than this human system could keep up. And so we were issuing quotas, and fishermen were staying within those quotas, yet overfishing was still occurring because the science wasn't able to keep up with the changes in the ocean. But I don't think it's all terrible. So I'm going to talk a little bit about the future of the cod, and this is where those climate models are going to come in. So this is where we are. The black line is our current level of spawning stock biomass. The dashed line is where management thinks we should be. This is the goal that the New England Fisheries Management Council has for this stock. Okay, so keep in mind that's about 55,000 tons of fish, where in the late 1800s we were catching 70,000 tons of fish. So there's been a very big change in scale in our expectations for this stock. But this doesn't include the impact of temperature. So if we add a temperature effect, we bring down our expectation for this stock because they're going to be less productive. So now we're going to project things forward. So if we allow a little bit of fishing and project under our mean warming from the climate model projections over this period, we actually can get an increase in the population. If we take but we never rebuild to that, what is our current target. But if we apply the same temperature to our reference points, to our management targets, we would actually say that we could rebuild this stock by about 2028. Okay, so not too bad, not too far outside of the 10-year horizon that's the goal in management right now. But that's only one temperature, and we know that there's a range of temperatures that we could experience. We could have cooler temperatures, right, where we are not the temperatures get cool, but we cool at a slower, or we warm at a more gradual rate. Or we could stay on this on our 30-year warming trend, which I'm calling the warm case down here. And you might look at this graph and say, wow, we should really be hoping for warm water, right? Because with warm water, we could say that we could rebuild a few years earlier, right? That we could declare victory and go home. Of course, it doesn't work that way. You have to take into account the temperature on the productivity of the stock as well. And so in the warming case, we wouldn't actually rebuild until about 2034. Okay, so there's this interaction between management and an interaction between the ocean. If there were no fishing, we obviously would increase the population faster, but at very large socioeconomic costs as well. So just a few lessons that I'd like to highlight. One of the things that I think we can say in the Gulf of Maine is that global warming is real and that it impacts things that we care about. It isn't just some abstract concept that's out there for people to talk about at wonderful universities like this. It's real and it's impacting people's lives. And we've seen that especially with the cod fishery, where communities in Gloucester are really grappling with a huge amount of socioeconomic stress due to the decline of that fishery. Lobster is sort of a different story, where we've seen basically the collapse of the fishery in Rhode Island and in southern New England. But in Maine, lobster is booming. The lobster fishery in Maine alone was worth over $500 million last year. Okay, a huge increase in the population, a huge increase in the value of that stock. And there's a temperature story that's embedded in lobster. We've seen northern shrimp. Very similar global distribution to cod, and not surprisingly, we've had a collapse in that fishery as well that's very much due to temperature. On the other hand, we're seeing an increase in species like black sea bass, especially here in Massachusetts. We're seeing longfin squid moving into the Gulf of Maine, and these are potential commercial species that may make up for some of the loss of some of these other things. So, the previous talk, I think, did a great job of sort of laying out the adaptation challenges that a city is having to deal with. We're trying to understand what are the adaptation challenges that fishing communities and that fisheries management has to deal with. And a lot of it has to do with thinking about decisions that get made by different actors at different space and time scales. So a fisherman has to decide whether they're going to stay in the fishery or whether they're going to leave. A fishing community has to make decisions about their infrastructure, right? They have to think about sea level rise, but they also have to think about, are they going to continue to support commercial fishing, or are they going to put in a marina and support yachts? For fisheries management, how can we account for trends similar to what we've done with cod? Is there a way to develop forecasts that might be able to give advice on the medium term about how to manage fisheries? and what are the strategies that we can take to manage for resilience. So just some quick summary points. The Gulf of Maine is warming rapidly. The warming has already impacted human and natural communities. The adaptation requires, first of all, acknowledging that climate change is having an impact. But good management can build resilience. So there is an opportunity to make sure that the fisheries that we have can be sustainable in a warmer climate, as long as we acknowledge that the climate is going to be warmer. So thank you.
Hi, everyone. It's great to be here today, so I want to thank the organizers for inviting me. And I also want to thank you for being here to share with us some of the work that we're doing to understand the impacts of ocean acidification on our marine life. My name is Anne Cohen. I'm from Woods Hole Oceanographic Institution. As we're pumping huge amounts of carbon dioxide into the atmosphere through human activities, we're not only warming the atmosphere and the oceans, but we're also changing the chemistry of the ocean in significant and measurable ways. And specifically, what I want to focus on today is the decline in ocean pH that's occurring as the ocean is taking up excess carbon dioxide. And this is a process, an ongoing process that is referred to as ocean acidification. But I want to start my talk today by introducing you, or reintroducing you, to two organisms that you know very well, but you might not recognize them because they were just born. They were just fertilized. So on the right here is the larva of shellfish, and on the left is a planular larva of a coral. That's what baby corals look like. They're just a blob of fat, not much else. And these babies are about 24 hours post-fertilization. And over the next 24 hours, they're going to do something absolutely remarkable. They're going to completely transform. The baby coral is going to transform into what we call a primary polyp. It looks not much different from a sea anemone. It has tentacles that have stinging cells that can capture prey. It has a central mouth. And underneath that polyp, a skeleton, a beautiful skeleton, is beginning to form. And this is within 24 hours of that larval stage. And that baby shellfish that you saw earlier is busy enveloping itself in a shell of calcium carbonate. And by becoming calcifiers within the first 48 hours of being fertilized, what these organisms are doing are joining a myriad and diverse array of marine organisms, plants, and animals that build calcium carbonate shells and skeletons. And there are ranging from microscopic plankton that are photosynthesizing and providing a lot of the oxygen that we breathe, to corals that are building geological scale structures that we know as coral reefs. And what all of these organisms have in common is that day in and day out, 24 hours a day, 7 days a week, 365 days of the year, they are pulling calcium ions and carbonate ions from the seawater, and they join them together to make calcium carbonate molecules. And from these molecules, they're building calcium carbonate crystals. And as you can see, the calcifying plant, this is Halimeda, kind of throws its crystals together all haphazardly to build its skeleton. When you look at the corals in the scanning electron microscope, they're a little more organized. They're building radiating arrays of crystals that are eventually going to build the coral reef. But nothing quite compares to the amazing organization of the mollusk nacreous layer, the layer that we know, that iridescent layer in the inside of the mussel shell. We can't build anything like this in the laboratory. This is a carefully organized process of calcium carbonate building. Now, from a calcifier's perspective, what you really care about in that ocean is the carbonate ion concentration. Because as you can see from this schematic that I've put together, there's a ton of calcium ions in the seawater. They're not going anywhere. But for every 25 calcium ions, there's only one carbonate ion. And it's actually really easy to change the carbonate ion concentration of seawater. All you have to do is change the pH. So here's a schematic of a pH scale. More basic on the top, toward more acidic on the bottom. Seawater before the Industrial Revolution, so this is prior to about 1850 when we started to pump a lot of CO2 in the atmosphere. The seawater pH was around 8.2. Carbonate ion concentration, very abundant in seawater. You can see that you just need to change the pH by about 0.3 units, not a big change, to more than half the carbonate ion concentration. How do you change the pH? A lot of you, if you have a soda stream in your kitchen, which I do, are changing the pH of your water every day by injecting a few squirts of CO2 from the soda stream bottle. But that's a bottle, a very small amount of water relatively. How do you change the pH of the global ocean? Quintillion gallons of water in there. Well, we're doing a pretty good job of it. This is a data set published by the Global Carbon Project, and they're keeping track of how much carbon dioxide we're emitting into the atmosphere every year. On the x-axis are CO2 emissions. Now, this is gigatons of carbon per year. A gigaton is 1 billion tons of carbon. And this is just the data since 1990, so the past 25, 26 years. And there's two things that I want you to notice here. One is the sheer amount of CO2 that's going in from human activities. 10 billion tons a year at this point. And the other thing to notice is that the pace or the rate of these emissions is actually accelerating. We're not slowing down. So that at this point, 2013, when these data were published, was the highest number of the past 25 years. Just to put that in perspective, you may have seen this plot earlier today. This is a 400,000-year-long record of CO2 concentrations in the atmosphere. And prior to very recently, most of that information comes from measuring CO2 trapped in bubbles that are trapped in ice cores. And what you see from this plot is that, yes, carbon dioxide concentrations in the atmosphere have changed quite dramatically over the past 400 years as the Earth cycles between glacial and interglacial periods. But here we are today. We are at the highest concentration that the Earth has seen in the past at least 400,000 years. And more recent data suggests at least 800,000 years. So the ecosystems, the marine ecosystems that we know today are adapted to these levels, not these levels and rising. Where does all this excess CO2 go? Well, the trees are taking up about 27% of those 10 billion tons a year. 47% is hanging out in the atmosphere, and that's what's causing the atmosphere to warm. And the ocean is taking up quite a bit, hundreds of billions of tons since the start of the Industrial Revolution, around 26%. Now, when the ocean takes up carbon dioxide, the CO2 doesn't just sit there. It actually reacts with water, with the seawater, to form carbonic acid. But the carbonic acid is not stable, and it dissociates pretty quickly into free protons, these H pluses, and bicarbonate. And the increase in these free protons is what is causing the pH to decline. But as far as calcifying organisms in the ocean is concerned, it is not so much this decrease in pH that's a problem. It's the fact that those free protons, a lot of them, go around like little Pac-Men looking for carbonate ions to bond with. So those few carbonate ions, at 10% of the total carbon in the ocean, exists as carbonate ions, are falling victim to bonding by these voracious protons. So what ocean acidification is the decline in pH, and at the same time, the decrease in the carbonate ion concentration. The ions that all those calcifying organisms, from the coccolithophores, to the lobsters, to crabs, to shellfish, to corals, to coral reefs, all need to build their skeletons and skeletal structures. Now, the chemistry of ocean acidification is actually pretty straightforward. You put CO2 into the water, it dissociates, it forms carbonic acid, dissociates, pH goes down, carbonate ion concentrations go down. We actually have, for about the past 30 years, moorings out in various stations around the world's oceans that are actually making these measurements in situ. And those data are coming back from various parts of the oceans, and what we see everywhere is exactly what we would expect. The carbonate ion concentration of the oceans everywhere has been declining for as long as we've been measuring it. What we do in my lab, and I don't do this alone, I have colleagues that I work with, both at NOAA, at Hui, and at other universities. What we do is try to understand not only the local processes that are exacerbating or modulating ocean acidification, but also how these changes are impacting the organisms that we care about, even those that we don't care about. Well, I think we care about all of them. I want to focus today on one of these organisms. This is the sea scallop, Placopecten magellanicus. You might know it from the grocery store. It's delicious, especially wrapped in bacon. I shouldn't say that. I'm a Cohen. But the sea scallop is one of the most valuable fisheries in the US. In fact, I think it is, at this point, the most valuable fishery on the US East Coast. It's about a $500 million fishery, employing thousands of people, from the fishermen all the way to the restaurateurs. So the scallop itself is enormously valuable. But it also is one of the major prey items of other valuable fisheries, such as squid, lobster, and the animal that Andrew was talking about, the cod. And Andrew, I don't think you took into account the impacts of ocean acidification on the cod's diet. But so impacts of ocean change on the sea scallop, for example, would have major ramifications, not only directly to humans, but also indirectly through its effects on other organisms. The sea scallop is abundant along the North Atlantic Bight and also in the Gulf of Maine, specifically on Georges Bank. We actually have data now coming in, largely through NOAA's efforts, on what the pH conditions in the Gulf of Maine are during sea scallop spawning time. So these are the actual data that are coming in. This is October, November, December on average, pH. And as you can see, that in some period of sea scallop spawning time, we're already at pHs that are quite low, so 7.85. You remember my earlier slide showing that you don't need to change the pH that much to change the carbonate ion concentration quite a bit. And by the time we get into this pink zone here, that is where the carbonate ion concentration is so low that we would expect the shells to stop dissolving at this point. So from these data, NOAA is actually starting to make projections under various emission scenarios about what the future pH in sea scallop habitat is going to look like. And this is one example. So for example, if we continue on the current emissions track, by 2060, the pH in sea scallop habitat will look like this, below 7.85 for most of the spawning time. And then by the end of the century, we're basically in a zone where for most of that spawning time, the pH is so low that the shells will start to dissolve. Why are we so interested in a spawning time? Well, it turns out that the adult shellfish and the baby shellfish make their shells out of different forms of calcium carbonate. The adult makes its shell out of calcite, and the baby makes its shell out of aragonite. And it does that because aragonite is much easier to make. If I was going to make a shell in seawater, I would choose aragonite. Much easier. I could just lay back there, just build my shell. No energy required. The problem is that it's easy to make, but it's also easy to take away. So aragonite is a much more soluble form of calcium carbonate than calcite. And that means that the baby shells are much more vulnerable to ocean acidification than their parents. Now, we recognized this fairly early on, that this is potentially an issue, but we needed to understand better in order to inform policymakers, to inform our colleagues at NOAA, what the sensitivity, potential sensitivity of these larval shellfish are to ocean acidification, because we have no idea. We know that if you decrease the carbonate ion concentration, they're going to have a harder time building their shells. We need numbers. So what we started to do was work with our colleagues at the Marine Biological Laboratory, bring in adult sea scallops from Cape Cod Bay, males and females, and entice them very gently with music and warm up the water a little bit, create some ambiance, entice them to spawn. And we had a few failures, more than I care to mention. But eventually we got this right, and we had fantastic success with spawning. We collected the fertilized eggs in a bucket. And then at this stage, at the trochosphere stage, we introduced our larvae into conditions in the lab that mimic the pH in 1960, the pH today, the pH in 2060, and the pH by the end of the century, to see how they deal with it. What's absolutely remarkable is that some of those babies, even though they're growing in conditions where the shells really shouldn't grow, and if they do grow them, they should just dissolve, there are some, a few percent in each batch, that manage to come out perfect. They just know how to deal with it. And this is something we need to figure out. How do they do it? But this is an absolutely perfect 9-day-old D shell. It's about 50 microns in diameter. Can't see it with the naked eye. We have to put it under the scanning electron microscope. Absolutely perfect. Grew in a pH where the shell shouldn't grow. But the problem is that the majority of those babies either don't form shell, or they form notched shells that can't close, so they can't protect the animal, or they're so deformed that there's no way that they're ever going to live to adulthood. So we can quantify those deformities, and what we see is that as we lower the carbonate ion concentration and the pH of our experimental water, the numbers of babies with deformities so severe that they're not going to, let alone reach adulthood, they're not going to metamorphose, they're not going to settle, increases dramatically. So by the time we get to conditions in the Gulf of Maine that are projected to occur by 2060, more than 80% of our larvae have deformities that are incompatible with life. This is a massive, massive impact. Now, some of my colleagues at WHOI and at Ocean Conservancy have been working with NOAA on integrated impact assessments. And what they do is they build a model, including various factors like how the pH is going to change, how fishing is regulated, to try to project the impact of ocean acidification and warming on biomass, on landings, on the economy that surrounds this fishery. So this is one plot that actually appeared in a recent paper led by Sarah Cooley in 2015. And this is the projection, biomass on the y-axis over time, up to 2050. If emissions stay at, or CO2 concentrations stay at present level, versus a business as usual CO2 emission scenario. So we keep pumping as much CO2 in the atmosphere as we are now. This is the projected decline in biomass in sea scallop habitat, with implications for impacts on landings. But these data, these projections, were made not with data from sea scallops, because we didn't have them at that point. They were made with data from oysters or estuarine organisms that are seeing naturally large fluctuations in the pH in the environment. If we put our data in there, the implications are much more stark. We're seeing a 50%, 25 to 50% decline in the biomass in sea scallop habitat just over the next few decades, just as a consequence of ocean acidification. And that's one organism that we studied. There are myriad organisms out there, a lot of them are, upon which we depend, not only for the oxygen that we breathe, but for the food that we eat. And we're just starting to understand and study the consequences or potential consequences of the ocean acidification. I want to end on a, although I don't feel particularly optimistic today, I do want to end on an optimistic note by reminding you that we do see some babies in our experiments that for some reason can deal with these conditions. So it's probable that there are populations out there that for some reason are adapted to dealing with much lower pH conditions. The target now is to go out and find them and then protect them to make sure that we have these organisms around for our children and our grandchildren. Thank you very much. Wrapped in bacon.
This is a very meaningful moment for me in many ways. I was born on Cape Cod and raised in a town called Wellfleet on an island called Boundbrook Island, where I ran free as a young boy over the hills, then barren of trees, learned how to find water and sand. And I grew up in an environment where we were surrounded by animals and wildlife. There was an old ship captain's parrot up in the grape arbor above the porch, goats, sheep, etc. So for me to be here today and to listen to people talking about the ocean is a real treat. And so before I really get into the presentation formally, I'm going to read you something from Aldo Leopold. And I hope to also give you a sense of who I am as a person, because I think the connections we all have in this room are in many ways driven by our connections, the affect, and the emotional connections we share, and our passion. This is from a Sand County Almanac. Some of you may have read this book. There are some who can live without wild things, and some who cannot. These essays are the delights and dilemmas of one who cannot. Like winds and sunsets, wild things were taken for granted until progress began to do away with them. Now we face the question whether a still higher standard of living is worth its cost in things natural, wild, and free. For those of us in the minority, the opportunity to see geese is more important than television, and the chance to find a pasquiflower is a right as inalienable as free speech. These wild things, I admit, had little value until mechanization assured us of a good breakfast, and until science disclosed the drama of where they come from and how they live. The whole conflict thus boils down to a question of degree. We of the minority see a law of diminishing returns in progress. Our opponents do not. That was written in 1949, the year I was born. You may have seen some connections to the situation today. Each day, our sun gives rise to a resounding chorus of life that continues around the globe 24 hours a day, 365 days a year for millennia. These sounds are not some random collections. These sounds are the living reflections of evolution's economy, the costs and benefits imposed by living in a biological and physical environment. I'm a bioacoustics engineer. It's a multisyllabic summation of who I am, I guess. I listen and study the sounds and songs of life in the air, on land, and in the ocean. My work has taken me from the Arctic to Argentina to the Central African Republic to some of the most remote places on this planet. In 1972, when I was asked by two of the world's leading whale scientists, Roger and Katie Payne, just not too far west of here in a town called Lincoln, I was asked to join them on a National Geographic expedition where they were about to start studying the endangered southern right whale. This was in Patagonia, Argentina. There's a beautiful picture of two right whales in shallow water. We lived in tents along this beach. We ate out under the Southern Cross every night around a campfire. And we awakened in the morning to the sounds of whales, sea elephants, and penguins. It was in this magical place that Roger explained to me his hypothesis that he had just published. This was in 1971, he published it. That prior to the advent of modern shipping and all the noise that ships make, the songs of blue whales and fin whales, these are two of the largest animals ever to live on this planet, those songs could be heard across an ocean. Now, I was a little skeptical that the songs of whales could travel thousands of miles across an ocean, or that the noise from ships could actually drown out those voices. But I was sufficiently intrigued that it changed the course of my life. So in 1992, I was given the opportunity, I was selected by the US Navy as their marine mammal scientist who would be given access to the US Navy's Sound Surveillance System. That was a classified term called SOSUS. But this was in a rather enlightened period in the recent political history of our country, when Senator Gore, Senator Kennedy, Senator Stevens, Senator Nunn helped form a program that we referred to as Swords to Plowshares. And the US Navy offered its SOSUS system as a way of studying marine life. So the first time I got into the SOSUS system to listen to blue whales, all I heard was a giant hum. So I thought my equipment was broken. I went around and tried to fix everything and make sure it was all plugged in right. And I knew it was working. I knew there were whales out there singing because I could see the voice prints on the Navy displays. And then it hit me. Of course, I couldn't hear a blue whale singing because my mind and my ears were completely out of tune and out of touch with the blue whales. But I knew how to fix it. I had to speed up the song, and when I sped up the song, voila, I heard the whale singing. So this is a voice print of a blue whale singing in the Atlantic Ocean. And a voice print is very much like a musical score. Time runs along the bottom from left to right, and pitch is low at the bottom and high at the top. Now in this case, pitch of 10 hertz and 20 hertz, it's below your hearing threshold. So this is why I couldn't hear anything. I just heard stuff, right? So I'm going to play this back to you at 30 times faster than I originally recorded it. When I first heard this song, the hair went up on the back of my neck, and I still get chills remembering that moment, because that was the moment in 1992 that I knew Rogers' hypothesis, as crazy as it was true. So consider this. A blue whale singing off the Grand Banks of Canada can be heard all the way across the Atlantic Ocean. It was in these early days in SOSUS that I met a young lieutenant named Chuck Gagnon. Chuck was a wizard at tracking submarines and at how sound travels in the ocean. So I asked him, Chuck, what would you do if you had a voice as loud and as low as a blue whale? He didn't hesitate to answer. He said, I could illuminate the ocean. Now you see what he did? He took the acoustic radiance from the voice of the whale and translated it into an image of how that image would allow him to see the ocean. So I said, Lieutenant Gagnon, so could you show me an image? Could you show me what this would look like? He said, sure. This is what he showed me. Okay? The tail at the bottom of the screen is where the blue whale is singing off of the Virgin Islands. The dark radial bands radiating out from the whale represent how loud the voice of the whale is throughout the western North Atlantic Ocean. Notice how those lines outline the continental shelf along the United States, from Florida all the way up to the Grand Banks of Canada. The blue dot in the middle is the island of Bermuda, and notice how the island casts a white acoustic shadow to the north in which no song appears. Notice to the right the jagged edges of the song outlining an underwater mountain range known as the Mid-Atlantic Ridge. Whew. I was pretty amazed, but I figured I might as well push my luck. So I said, okay, so Chuck, can you actually follow one of these whales and track it throughout the ocean? He looked at me and he said, piece of cake. Right? This is an animal putting out 185 decibels. This is 6 orders of magnitude greater than a submarine. So a few months later, Chuck showed me this track of a blue whale he called Old Blue. Right? Old Blue was a male singing across an ocean to find a mate. Chuck tracked Old Blue for 43 days as it sang and swam 1,700 nautical miles. That's pretty much the distance from here to California, all right, throughout the ocean. So this changed my perspective and started to change my perspective on space and time. I couldn't hear the whale, so it wasn't there. I couldn't see the whale, so it didn't exist, okay? But we had this system in which it was exposed. This is a 1-year voice print from the Pacific Ocean, halfway between San Francisco and Honolulu. 20 at the bottom, 20 hertz, is the lowest pitch that humans can hear, and 440 is orchestral A. For those of you, I presume there's some musicians here, I hope, right? Yeah, right, that's orchestral A. The yellow striations dripping from the top represent the energy from ocean storms, and that glow you see in the lower right represents the collective voices of singing blue whales and singing fin whales. That chorus lasts for about 3 or 4 months, from September into mid-January. So again, what I'm hoping to show you is scales, right? Ocean scales. Biggest animal on Earth, big scales. Low voice, very, very loud. These are the kinds of insights you can get into the scales. Chuck and I have been working together now for about 26 years. We're still doing this. And it was Chuck who taught me to think of the SOSA system as an acoustic telescope, right? He discovers interesting objects in the telescope's visual displays, and I drill down into those voice prints to listen and discover what they are. These discoveries span enormous periods of time and space, okay? So I can actually track whales throughout an ocean basin for months at a time. And this is a really important point I want to get across to you. This fulcrum of awareness took me from knowing something, and Anne, this is something we were talking about earlier, it's you know something because you read in a book. I took classes. I was a postdoc. I was a graduate student. I had all the epaulets and the things that you wear to show how cool you are. But until I actually experienced this, I had no idea, really, no understanding of the scales of space and time and frequency which were operating in the ocean. Not in Cape Cod Bay. I love Cape Cod Bay. I love Gulf of Maine. I love Western North Atlantic, but it's the ocean. And I have to tell you, I basically grew up running around in Cape Cod, and I'm in love with the living world, okay? I have a love affair with the living world. I'm very passionate about it. So what I've played you the song of the blue whale, and I'm going to play you some other songs of whales in the ocean, or sounds of whales in the ocean, because I want you to be aware of this sort of quick holiday tour of the voices of the animals. The blue whale is infrasonic. I'm going to take you all the way up to the beaked whales, which are working at very high ultrasonic ranges. This is a voice print of a bowhead whale. A bowhead whale, this is an Arctic species. It's the right whale that went north and never came back, and it lost all of its mascara and makeup, right there, no markings on the head. This animal sings with 2 voices, and this is what you hear if you take a paddle and you put it against the ice. This is one animal. We still don't know how they make these sounds. Okay, now I'm going to play you sounds from a collection of melon-headed whales bouncing over the highlands in Autech down in the Caribbean. These are mostly ultrasonic, but a lot of the voice is in the audible range. And what these animals do, these are highly fission-fusion societies. They are constantly inventing new sounds. So an individual in a group bouncing over the highlands, I think of Monty Python, right? Click, 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 And they're inventing sounds all the time. It reminds me of someone outside of Grand Central Station blowing up balloons and twisting them into little animals and handing them off, right? Just making things. And I will make something, and then John, you would imitate it, and then Andy would imitate it, and this is our social currency. This is how we maintain our social group. Because remember, the blue whale is 90 feet long. It can barely see its tail, but it can communicate with another whale 3,000 miles away. A herd of melonheads, which might be bouncing over the highlands of Cambridge, Massachusetts, the way they communicate, the way they maintain their social structure is through sound, okay? So they're constantly playing with sound. They're highly social animals. Now I'm going to play you the sounds from an echolocating, foraging beaked whale. This is an animal that dives 1 mile down into the ocean, okay? Hunts in complete darkness, trying to find bags of water called squid. And that's how it makes its living, right? So it's sending out slow pulses just like a bat. And then, like that, that's what the squid hears just before the... Okay? That's it. That's pretty much what these guys do. But this click that I'm playing to you at fast, this comes from a device that was attached on the back of the animal. It's ultrasonic. It's living in a space of sound that you and I can't hear and we can barely appreciate. Space. I'm going to now show you an animation of fin whales, singing fin whales, males. You see where we are? There's Nova Scotia, right? Okay, there we are, right here. We're sitting right there. Okay, so these are, I'm tracking singing fin whales. I'm not seeing them, I'm tracking them. And so you're gonna, and I'm animating it. So I'm showing you over time, and your eye will see tracks. This is their space, all right? 100,000 square miles, 200,000 square miles. They don't live in these little places such as we observe them in. If you go out on a whale watching cruise and you see some whales, you think, oh, there they are. It's much bigger, okay? So this is their space. Cape Cod Bay is where we work, so we put in an array of underwater microphones. This is my poor man's U.S. Navy array in Cape Cod Bay. And here's what happens when we track right whales. This is happening at night, mostly. And what you're going to see is you're going to see some little worms move around. That's these animals calling back and forth. They call antiphonally. They maintain their social cohesion with sound, okay? There is that little insight into their 3 days in the life of right whales. We may have only had 20 whales in the bay, but they're acoustically extremely active. So the point is, acoustics is their world. Okay, this is how we, as a scientist, I try and represent what I hope you experienced in terms of listening to it in that spatial scale into a three-dimensional space, which is defined by frequency, the pitch of the sounds, the range over which these animals are using those sounds for maintaining communities, communicating, navigating, finding food, defense, and the time over which they use these. So notice that here's the blue whale, this little jujube up here, and here's the beaked whale, restricted down here in this space-time frequency domain. All marine animals studied to date, whales, seals, fish, shrimp, all produce and use sounds for all the basic activities of life. Communication, navigation, defense, finding food, maintaining social networks. Acoustics is the modality of choice. It's very efficient. Light does not transmit very far at all in the water. You can't use these big acoustic telescopes without being brutally aware that all of our activities in the ocean, human activities in the ocean, are creating a din, a lot of noise. We use sound in the ocean. Humans use sound in the ocean for all of our basic activities in the ocean. We use sound for communication. We use sound for navigation. We use sound for defense. We use sound for finding food, okay? Another ways we use sound is we use sound to find oil and gas hydrocarbon deposits beneath the seafloor. So I'm going to play you the sounds of an air gun array in which we set off explosions every 9 to 10 seconds for many weeks and many months at a time. These are very, very loud. They're so loud that they basically boil water, right? They create a partial pressure. Okay. You also hear the sonar pings from the ship's navigation system. So off of Boston, we've had an LNG terminal built, and one of the questions was, in all this noise that we're generating by our shipping and our LNG terminals, could that be affecting the acoustic ecology of our endangered right whales? So here I'm going to change my pitch a little bit, and where I'm going to appeal to people who are creative artists, who are videographers, who translate science into visualizations that people can understand. Because one of the most difficult concepts that I've had is the acoustic footprint of a ship or the acoustic footprint of a seismic survey vessel, right? So this is a visualization where this sort of Starry Night Van Gogh, these dots represent the acoustic space of an individual right whale that's communicating with other right whales, right? These larger meteorite things, these are the footprints of commercial ships. This is where the LNG terminal was. So right now there's an LNG ship on this date and time that's offloading LNG into Boston. This is a small boat, relatively small boat coming out of Boston. There's some off Gloucester. That's a commercial ship. So I'm going to animate this. This is real data. We had 19 recorders in the area for 5 years. We know the ship speed. We know all the information about the ship. We know the noise footprint. We know the whales. So I'm just animating this. And what you're going to see is the footprints of the ship traffic. This is just commercial shipping coming in and out of Boston. And when the light of the whale disappears under the footprint of the ship, that whale loses all possibility of communicating with another whale. And what this has led us to model is that these animals are losing over 65% of their opportunities to maintain communication system. That is, we are constantly tearing and ripping apart their social mechanisms for maintaining communication space. Seismic exploration. This is a big issue because there's been a strong effort to open up the East Coast all the way down to Florida to seismic exploration. Yep. Here's a visualization of a seismic exploration activity's impact on 100,000 square miles in the ocean. These red dots that you'll see the flashes represent singing whales. Here is when I now put seismic surveys and ship noise into that map. Notice the scale, the space that is occupied by the shipping noise and the seismic surveys. It's enormous. So this is an attempt to quantify and create a model by which we can assess how noise in the ocean is actually impacting the ecological systems of life in the ocean. So why should we care? This is similar to other questions we've heard today. Why should we care if all the noise we're making in the ocean is impacting ocean life? I have a hypothesis. It'll take me 2 minutes. But as Chuck was using the acoustic telescopes to look into the ocean for interesting objects, he discovered a phenomenon. It was an acoustic glow of energy that showed up in the voice prints. This glow showed up after sunset and lasted for many hours before going away. When I listened to it, there was nothing there. But we knew it was there because we could see the glow in the voice prints. It turns out we were listening to sea anemones, thousands and thousands of sea anemones scraping algae off rocks along the coast of a coral reef where we were pointing the telescope. This made us very interested, and so Chuck continued to look for other glows of acoustic energy that we could not explain. And he found one. And it wasn't sea urchins, because this time he was pointing the telescope into the deep ocean where there were no islands, there were no coral reefs, there were no sea anemones. I think I know what it is. I think we're observing a phenomenon that happens every day when billions and billions of tiny organisms, some of them surrounding you on the walls or in this room, and you've heard about today, move up toward the surface of the ocean at night and then descend and disappear into the depths of the ocean during the day. Every day, 365 days a year, but for millions and millions of years. This phenomenon was first detected by the US Navy during the Second World War using anti-submarine sonar. It's called the deep scattering layer. We are detecting the deep scattering layer in the voice prints when the ocean is quiet. These organisms depend on tiny, microscopic exotic forms of life, such as you see here on the walls, that convert carbon dioxide into oxygen. Okay? You've heard about this. And I think everybody in this room now knows that every other breath you take comes from this phenomenon, the respiration of these organisms. So we are literally witnessing the voice of the living ocean breathing. This is more than amazing. This is literally our breath of life. We are wise to pay attention to the light we can't see, to the sounds we can't hear, and to the life we know is there and on which all our lives depend. Thanks very much.
Thank you very much, Dr. Clark, and to our whole panel for these excellent presentations. So now we have time before our final session, we have time for 2 questions from the audience.
Adam Sachs again, since nobody else is here. I want to ask Dr. Clark about your findings among the animals whose shells are just being defective. Aren't we seeing natural selection right in front of our very eyes there? And over generations, have you done a longitudinal kind of study over generations of those creatures? I don't know if it's possible. And see if you develop a population that's resistant to acidification.
I think the question is for me. Yes. Is this on?
Yes. Yes.
That's a really good question. I think humans are definitely performing a natural selection experiment. The question is it going to work? I mean, the level of uncertainty there, I think, is one of the scary parts of this. Natural selection also usually happens over very long time periods. And what we're doing is really escalating the rate at which things are happening. As far your question with respect to have we grown these organisms out through several generations to see if natural selection can occur, not with the sea scallops. In fact, Ours was the first successful experiment, ocean acidification experiment with sea scallops, just because they're so difficult to rear under experimental conditions. And so we actually invested several years into figuring out how to actually grow them in the laboratory so that we did have a successful grow out under ambient conditions, and then started to introduce them to treatments after that. So in fact, even though I'm sort of showing the end result of these experiments, it takes a long time, a lot of effort, quite a bit of money to come up with really robust results that we feel confident that we can put into these projection models. So we're kind of at the cusp of this. There also isn't an endless amount of money. This is another thing you have to understand. I mean, NOAA, who is running the ocean acidification program, who actually funds our sea scallop experiments, they're cut. And funds are thin, spread thin on the ground. So we've submitted a proposal to an open call to do exactly that, to test out different populations of sea scallops, to see whether we can see natural variability and sensitivity across different populations. I'm going to have to submit that proposal again.
Right, but I mean, they're not going to wait to evolve for you to get, funded. I mean, I absolutely support the study. But if the acidification is increasing, then you're going to get that selection. It's going to be gradually increasing along with the increasing ocean acidification. And evolution, with fast-growing animals, I mean, we see these things with industrial moths in England and that sort of thing. They change pretty quick. And I don't know what...
Well, we have examples from history, from geologic time periods, of mass extinctions of calcifiers under elevated CO2 conditions. We know that these things have occurred at least 6 times in the past. Right. But the time scale for those organisms to come back is a hell of a lot longer than you're going to wait around for the sea scallop in the restaurant.
Right.
Tens of thousands of years.
Well...
So we're talking about a brink of a mass extinction. Organisms, yes, they're going to come back. Some organisms are going to adapt. But the time frame that we're looking at is not the time frame that we are operating on.
But what's their reproductive cycle? I mean, you have 10% of them who are surviving, and they're the ones who are going to reproduce. Oh, ask it later.
Yeah. We're going to move on to our last question. Thank you.
We can continue the conversation.
I just wanted to ask Dr. Clark, I see Cornell on your resume, and I was wondering, could you tell us one anecdote about the most amazing thing you heard from birds?
Dinosaur call.
Yeah, that's good. Dinosaur calls.
Right, thank you again to our speakers.
Musician Wren.
And to all of you for the wonderful session and symposium so far. Thank you.